Good afternoon, everyone. I'm Yu Mu, the student host today from the Center for Integrated Catalysis. So it's my honor to introduce Professor Lang Luo to you. Professor Luo was born in China and obtained his Bachelor of Science degree in Applied Chemistry at Beihang University in 2009, where he worked on electrochemical detection of parts per billion copper ion based on the self-cleavage of specific DNAs with Professor Lidong Li. Then Professor Luo studied nanomaterials for electrochemistry systematically at the University of Utah with Professor Henry White. And Professor Luo got his PhD degree in analytical chemistry in 2014 before moving to the chemistry department at the University of Texas at Austin as a postdoctoral scholar. Professor Luo spent 3 years in Austin collaborating with Professor Richard Crooks to develop characterization and application of nanomaterials and joined in the Department of Chemistry at Wayne State University in 2017. Now, Professor Luo is the Carl Johnson Assistant Professor in the Department of Chemistry, and Professor Luo's group is focusing on developing new frontiers in electrocatalytic and electroanalytic science. Today, Professor Luo would like to give us a presentation on rational design of alternating current electrolysis for organic synthesis. Now let's focus on Professor Luo again and enjoy his talk.
Okay, thank you for the introduction and thanks for the invitation. Let me share my screen. Okay, can you see my presentation? Okay, good. So
looks good.
Okay, so let me change my laser pointer so you can see my laser pointer. So today's talk will be on my recent work on rational design of alternating current electrolysis for organic synthesis. So you can see in the title I highlight the rational design, because I think this is very important, and I'm going to explain to you why. So our group is not first one, who start developing alternating currents electrolysis for organic synthesis. Actually, this field has a long history. So so the oldest literature I found was back in the 1884, and then this literature actually is not in English; it's in German. And then they describe electrolysis with alternating currents using electrodes made of different materials to do this conversion of phenol to phenol sulfate. And I just give a context what this time really means. So here is some history of AC power. So back in 1886, this is actually the first full AC power system in the world was demonstrated. So that means since the first AC power system is available, people start using AC to do organic synthesis. And then there's a long history here. But even though these first attempts was happened like 130 years ago, but not much of progress in the past 100 years. I did some literature search. It turns out it probably has about 20 publications when we started, before we started here, and a lot of them actually were in German. And then so in the 50s, 80s, there's some papers out there, but not much. So why? It seems that AC is very kind of naturally transition from DC. Why not many people are using this AC for organic synthesis. So, I did some analysis. I realized that probably two main reasons. The reason one here is, people did not find any very useful reactivities of AC. So actually look at this paper. This paper was published in 1939. So, so the conclusion they had here is, the experimental results shows that the AC electrolysis, in general, so far as the final products are concerned, is in similar, results as the DC condition. But let me see, there's a chat here. Oh, okay, it's not for me. And then, the oxidation is slightly more favored over reduction. The reason for that is because when they did this reaction was done in aqueous solution. So the reduction side is this, hydrogen evolution. So, the oxidation will be more on the starting material. So, since, AC and DC give us pretty much similar results, why do you want to use AC? Sorry, stop here. So this is one of the paper in the 1982. So they also observed similar results. So what they did here was they electrosynthesize propylene oxide using alternating currents. So what they're trying to do here is they are trying to oxidize chloride to bromide to bromine, and the bromine react with this propylene to do chemical reaction. And then, the other side, when you switch the potential, you reduce water to generate OH minus, and then the OH minus reacts with this, brominated alkene to generate this, epoxide. So these results are actually, can be done. You say, you can see you have different frequencies, but the result here is actually kind of funny because when they have higher frequencies, the current efficiency actually decreases. And then, you actually have the best results when you only use the, DC condition. So that's just demonstrate that, using AC and DC does not really change too much of the outcome of a reaction. Instead, AC actually makes things worse in terms of current efficiency. So that's why, people say, we don't have any new reactivities, and then in terms of efficiency, even worse than DC. Why do I want to use AC? And then the second reason here is, the inherent complexity of, AC electrolysis for organic synthesis. Think about for traditional chemical synthesis, a lot of papers are there. And then, what they do is they start with some optimization table. So here I just found a paper, it's just a very recent JAX paper. So I just counted how many, condition they, kind of tried here. So this is just typical chemical reaction. You have some chemical reagents you can optimize. So this is like probably 4 different choices here. And then you have ligands because they use this, copper as the catalyst. They have different ligands. So these ligands have like 3 different choices. And then, this is the, reagents, the ligand, and then you have different solvents. This solvent, they try like 2 or 3 different solvents. And then, here they use different, copper salt precursor. So in this simple reaction, chemical reaction, they optimize 4 different, parameters. And then if we just simply count the possible combinations, we get about 108, possible combinations for reaction optimization. Of course, in this paper, they do not really try all the possible 100 plus, condition combinations. They try to sum and then gets the result. Here, I'm just showing the total possible combination. So this is the typical chemical synthesis optimization. For electrochemical synthesis optimization, the space is even bigger because now instead of using some typical reagents, you're gonna put some, electrodes in there, some electrolytes in there. So they just increase the parameter space. Here's another JAX paper, fairly recent paper. So what they're trying to do here is they did this diazolation reaction. So here they actually have to change different, electrodes. So they switch between, nickel and platinum are 2 choices of electrodes. And then they also need to worry about electrolytes. What can electrolyte, the effect of electrolyte. So you use 2 more choices here is lithium perchlorate and TPA-PF6. And also, it has to do with the voltage, because when you apply a different voltage to different currents, that will be different. So here they try like 2 different voltages, one 2.7 and 3.4. So these are just on top of the chemical parameters in the optimize. You have additional 3 more. So if we consider that, and each of the electromaterials, electrolytes, and a voltage, and we each have just 2, it ends up with 8 times more combinations. the total combination will come to 864 combinations. So this is just routine constant voltage electrolysis reaction. But if you think about if you're going to do AC, we have some complex alternating currents waveform. You have two more parameters. One is the frequency, right? So you can apply different hertz, right? From 1 hertz, 100 hertz, 1000 hertz. You have frequency choices, and also you have a lot of waveform choices. You can be a sine wave, complex wave, square wave, triangular waves. So all these things will affect your system differently. So if you take into account all these parameters, the parameter space you're going to be over thousands or several thousands of combinations. This is with this kind of parameter space, well, on one hand is good because you have more controls, that's things you can tune. But on the other hand is you just have a huge parameter space that makes things really complicated. So that's the two main reasons why AC really never become popular, because these two reasons. So if we really want AC to be popular, first of all, we need really to address these two issues. We need to discover useful, if possible, unique reactivities that cannot achieve otherwise. And second is we have to simplify reaction optimization. If possible, we want to rationally design them instead of just explore the entire parameter space, because that's going to be costing a lot of resources. So where do we start? When we first started, we did not really think about a lot of these kind of challenges associated with AC. The whole reason we started just simply because I went to a electrochemistry Golden conference, and then the conference organizer invites some really famous organic chemists who present their work on electroorganic synthesis, and then they showed a really impressive results, and then they published in Science and Nature. As an assistant professor back then, I was very kind of motivated. I thought I can do something that's related with electroorganic synthesis. Probably someday I can publish in Science and Nature. So. But yeah, I want to do electroorganic synthesis. But the question I had when I started was, what kind of reaction I should do? Because there's a lot of reactions out there. So what reaction should I do? So what I did here was, I first went to this really famous review article written by Phil Barron and his group. So in this paper, they summarize over 1,000 reactions, electroorganic synthesis reaction developed between 2000 and 2017. So it's such a long paper. I did not read the entire paper, but I did something, kind of differently, and I kind of did some statistical analysis. I realized about 70% or 17% of reactions out there are analytical reactions. That means you just have some starting materials, apply oxidation potential, oxidizing potential, and then turn into the product. About 20-something percent is about cathodic reactions, just reduce some reactant to get a product. Only about 20 examples that is really for this pale electrolysis that's used both electrodes to do electroorganic synthesis. As an assistant professor, I did not really want to jump into this too crowded area, so I started thinking about what I can do with this pale electrolysis. So for pale electrolysis, that as I said, you're going to use both electrodes. There's 3 types of pale electrolysis. The first type is called separate reaction, just like you have a membrane, you have 2 electrodes that's separated, and then they do separate things. They don't talk to each other. And then you can combine whatever 2 reactions you're interested in, putting in a separate reaction cell and then do the conversion. The second type is called sequential reaction. You have just one starting material, and then you let it reduce first, for example, and then from some reactive intermediate and oxidize it, and it gets the product at the end. So that is sequential. That's what I call sequential reaction. The third type is called convergence reaction. You have 2 reactants. One get oxidized to form some intermediate. The other one get reduced from some intermediate, and then these 2 combine and gets the final product. So this pale electrolysis, kind of reaction is very interesting because it provides some unique reaction environments where both oxidation and reduction can take place in the same pot. And then now we are not wasting one electron doing nothing. and then you have much higher, energy efficiency because you're using one electron to do two reactions in the cell. But the limitation here is you have very limited reaction library. So you don't have many reactions that really can be done using electrolysis. So I start asking myself, what kind of reaction requires both oxidation and reduction? So this photoredox catalysis idea came to my mind. So if you're not familiar with photoredox catalysis, here is very classic example. So what this example shows is, we start with this ruthenium photocatalyst, and then you shine light it, and it become, this excited states become, some strong reductants, and then reductants can reduce some starting materials. In this case, a triple chloride, and generate some CF3 radical, and itself become this ruthenium oxidant, and then you do another oxidation process and return to the ground states. And at the same time, intermediates react with the arene from some, arene radical, and then the diene radical, and then just oxidize from this final product. So if you're not very familiar with this photoredox catalysis cycle, don't worry about it. I have a simplified version for you. So what do we have here? You start with A, is ground state, and then you excite it, and then from A start. So the A star, the electron is as higher energy they want to leave. So typically the excited states are reductants. You can give out one electron to some substrates, and because this excited states lose one electron, itself becomes something like A plus, right? Because you lose one electron, and A plus one return to ground state. That means you're going to grab some electron from other place. So you can see in this catalytic cycle, you are doing reduction of oxidation sequentially. So we had a hypothesis. We thought, photoredox catalysis doing oxidation and reduction, sequentially, and then our electrolysis doing similar thing. So the hypothesis is, we think that we can perform photoredox catalytic reactions using electrolysis without using a photocatalyst. So here's what we did. This is the same reaction as I showed you earlier. So in this case, what we did here, we just use the same reaction conditions that photoredox people use, but we did not put any photocatalyst in the system. So what we think will happen is our cathode here, we're going to first reduce this triple chloride, and from some radical intermediates, and the radical intermediates will go to the other side and get oxidized from this carbocation, and then eventually from this kind of tetramethylated product. So did this reaction work? Yes and no. It sort of worked, but the yield is very low. It's only like about 13%. So when I showed this result to my organic colleague, he told me that anything that's had yield lower than 40% is just pretty much useless. So it turns out like kind of we developed some useless reaction. So it seems that it did not work really well. So how can we address that? So, we had a hypothesis. We think the reason why we have low yield is probably because the short-lived intermediates generates in reaction cannot survive in the mass transport in a process between two electrodes. So, here's some simple calculation from diffusion, equation here. So if we have a gap, a electron gap of 1 centimeter, it take about, if you just pure diffusion, take about, 50,000 seconds for molecule to move from one side to the other. So if you have just 1 micron, it still take about 0.5 seconds. So, if you want to have even smaller gap, it's going to be kind of go to nanofabrication, which is not trivial. So a lot of the reactive intermediate generated electrochemical or organic reaction cannot survive for the diffusion process. That's why we don't get a really high yield. So how can we address that? So we came out with this idea, and why not we apply this alternating voltage? So first of all, we have the starting material, and we apply a negative potential to it, and we can reduce it. And for some intermediates, right? This intermediate stay as the diffusion layer, all right? And then you don't go to the other side, you don't have to. And then we immediately flip the polarity of the electrode potential, and then we oxidize this intermediate to the final product. So in this way, the intermediate don't have to travel all the way from one electrode to the other, so they can be effectively captured and converted to the final product. So we try this. So this is the setup, very simple. We just have this AC waveform generator, and then we have 2 electrodes set up, And then, we just, apply this AC voltage as these two electrodes. And then we think what's going to happen on the same electrode, we're going to sequentially perform this reduction of triple chloride to generate CF3 radical and generate some intermediates radical. And then we oxidize it to form this final product. The cool thing about this kind of setup is, this system is sort of symmetric, right? So the stuff that happening as one electrode is going to happen on the other electrode. The only difference is they're going to be off, by half a period, because when you do oxidation on one electrode, the other side have to do reduction. But the overall reaction will be the same because they just both are doing sequential reduction or oxidation. So we tried it, and this is the result. So we found that this is the DC condition when you have a constant voltage, the pair electrolyte setup. We only get about 13% conversion. But when you add the right voltage, 4.4 volts and 100 hertz, we get 100% conversion and 84% yield. So remember, when we did this reaction, the only thing that we made changes here is just we apply a frequency so that we can capture the intermediate effectively without losing them during the transport process between electrodes. But when we look at the result, we was very confused because this voltage seems to really, really high. We have 4.4 volts. None of the solvents, organic solvents, can ever survive. So why that's high voltage and why 100 hertz? So to answer that question, when you first off find out what's the thermodynamic required voltage for this reaction. So let's go back to the fluorocatalytic cycle because our chemistry is very similar to the fluoro redox reaction. So based on their number, if you really want this reaction to happen, you need to have some reductants that's have potential minus 0.9 volts versus SCE. And if you want to oxidize something, you have to apply voltage about plus 1.3 volt, C1 volts versus SCE. So if you think about this as a reduction side and this oxidation side, and the voltage that's really required to complete this chemical transformation will be only just 2.2 volts. Okay, and then this is just the applied voltage sort of by this ruthenium photocatalyst. But the true thermodynamic voltage required for this transformation is actually determined by when this triple chloride get reduced and then the radical get oxidized to carbocation. So this one is only like 80 millivolts. Okay, here's the issue. So it turns out 2.2 volts should be enough to drive the reaction. Why do we need 4.4 volts in our AC system? Something's going on here, and we have to address it. So one of the potential difference between our system and their system is they have different substrates. Okay, so to find out what's the voltage required for our substrates, we have to measure that. So as I said previously, our reaction actually goes through these 4 steps. This is ECEC step, reaction mechanism. E stands for electrochemical, and the C stands for chemical. So you first reduce triple chloride to form this CF3 dot, and then these CF3 dots react with this pyro, and then form this kind of radical. And this radical get oxidized. This is another electrochemical reaction, the oxidation side, and then eventually to depollination for each product. So the voltage required for this transformation to complete depends on these 2 electrochemical steps. To find out the reduction potential for this guy here is easy. You just have this starting material in a solution, apply a negative potential, and see where you see the peak. Okay, and then from these results, the peak potential here is about 0.97 volts, because this is just where roughly this current start taking off. So you can estimate where this potential is. Okay, so this side is easy, reduction side is easy, but oxidation side is more tricky because this one here is not a real starting material. It's something that's generated during the reaction. It's the intermediate. So how can I tell what's the oxidation potential for each guy? So to do that, actually we did some thing called linear sweep photometry. So we hold the potential as negative enough potential here. So that's we reduce a whole bunch of triple chloride and from CH3 radical. CH3 radical is very reactive. It's going to react with this pyro and generates a lot of these intermediates. And then once we accumulate enough of these possible intermediates, we're going to sweep these potential really fast so that we can oxidize some intermediate being generated. So here you can see this is the result. So if I hold the potential as minus 1.2 volts, which is enough to generate a whole bunch of CH2 radical, as well as this, pyro radical, and we scan it, we can see like, sort of two peaks. And then, we hold at different times that we can control the different amounts of CH3 dots being generated. And you can see the waves increasing, right? So you can see this peak actually, there are two peaks that are increasing. One is this guy, the other one is that one. At this point, we don't know which one is which one. And then, but we do see some oxidation peaks appearing. That's just associated with some intermediate oxidation. But how can we tell which one is really belonging to this intermediate oxidation? So what we did here is we add a different equivalence of this, pyro to the system. So if the oxidation is truly coming from this radical, the generation of radical should be, depends on the starting materials of pyro you put in it. So what we found here is if we add different equivalents of the pyro, the second peak here increases more dramatically. So we kind of assign the second peak here as about 0.5 volts-ish to be the oxidation peak for this reaction. So, now we figure out the oxidation potential and the reduction potential for this entire, conversion, need. And then, minimally at least in the 0.85 volts, that's is where you see this current start taking off. Okay, so now based on these 2 volts here, the potential here, as 1.4, 1.5 volts should be enough, right? You don't need to go to 4.4 volts. Why? Why do you need such a much larger voltage for things to happen? So later we kind of figure out the reason. There are 2 main reasons here. The first reason is, our wave generator is not an ideal power source. Remember, we just use this guy to supply the voltage to drive the electrochemical reaction. But when we really measure the voltage that's outputs from this, this waveform generator, even though we set up to be 4.4 volts, the true voltage we can monitor here is about 2.2, 2.5 volts. This is just because the AC powerful AC waveform generator itself is not the ideal power supply. It has some internal resistance. You probably have, still remember this kind of a circuits you probably learned in the physics class in high school or middle school, whatever. So some non-ideal power supply has some resistance. You're going to share the voltage that you can output. Okay, so that's the voltage drop that GPU have. So we lost about half of voltage because our AC waveform generator is not ideal power source. And the second reason is, is because electrical doublet charging and IR drop in a solution. So here is sort of like equivalent circuits for our entire setup. So we have 2 electrodes, all right, and then we have solution in between them, right, electrolytes in between them. So as this electro-liquid interface, we have this electro-double layer, and then we also have the electrochemical resistance. And the solution is in here, and then on the other side is symmetric. So when we apply a reissue pulse, right? So what's going to happen is this electro-double layer capacitance, it's going to pass most of the currents, right? And the impedance from this side will be really small, and the currents will be fairly big. And it's going to pass a lot of current, through the circuits, and you have a lot of voltage loss because this solution resistance. And actually, we kind of can simulate the voltage loss during this charging process. So, for example, when we apply, 4.4 volts from our AC power supply, the true voltage we apply is 2.5 volts. But when you apply reissue pulses like what we have here, let's say we have 5 millisecond pulse, the voltage maximum it gets is 1.5 volts. Okay, so these 2, effects really reduce the true voltage that we can harvest to drive our electrochemical reactions. And then we have derived some equations, and we was able to figure out the true electrochemical voltage we supply to the electrochemical system to drive these AC electrochemical reactions. And then, on the different conditions, as you can see here, we have different conditions. You have 100 hertz, different voltage we apply, and 4.4 volts, different hertz. And then we have some like, dash line here, different zone here. So if we have voltage lower than 0.75-ish voltage, there'll be no reaction because it's not enough to drive the reduction of triple chloride and oxidation intermediates. And you don't want to go beyond this 1.5 or 1.6 volts because that's just going to direct oxidize your prior starting material and cause a whole bunch of cycle reaction. You can see the best condition is 4.4 volts because just slightly lower than the voltage required for cycle reaction, but it's as the maximum kind of efficiency. That's why we kind of get the best results as 4.4 volts and 100 hertz. So with this electroanalytical analysis, we can accurately predict the voltage and frequency combinations to do the reaction. So when we first demonstrate this chemistry, we were very excited because we can now do full redox catalytic reactions without using photocatalyst. And this is a big deal to us because photocatalysis, they're fairly expensive for common ones. So the most popular ones are these ruthenium and iridium ones. So for the simple ruthenium ones, it still costs more than $100, and for the fancier iridium ones, it costs close to about $1,200 or $1,300 per gram. So give us some reference. For pure gold, it's only like $60 per gram, and for uncut diamond, it's only like $7,000 per gram. So this catalyst is super expensive, but now we can do the same, chemical reactions, chemical transformations using just 12 cents per kilowatts electricity. So we were super excited, but we had some issues when we were trying to publish our paper because the editor thought, we don't have all new, unique chemical reactivities because we kind of borrowed the idea for the full redox catalysis and it just apply to our system, but which I don't really agree, but that's fine. So if they want unique chemical reactivities, we have to supply them unique chemical reactivities. So we went back to our drawing board, and then we kind of draw this photocatalytic cycle and our AC system. And then when I look at this, actually we realized one thing. The difference between our two systems is, for the photocatalytic cycles, it's sort of kind of fixed. The turnover is kind of fixed. The reason I say that is because the redox potential of a catalyst is kind of fixed. You can, of course, tune that by do some molecular modifications, but that's not trivial. And also, once a catalyst finished doing one reaction, it's immediately ready for the next reaction. You don't have much control over this process, okay? But for us, for AC, these two things can be very easily tuned. You can tune the potential, right, by applying different amplitude of AC waveform, and you can tune the time, durations of the pulses very easily by tuning the frequency. So that's give us a lot of control over, controlling, tuning the reaction kinetics. If we can, control reaction kinetics, that means we can, control reaction selectivity. So we imagine as if we have some, a reaction that can lead to product A and B, and we can probably use a frequency, and we just tune the AC frequency knob. We can switch it from product A to product B. That'd be pretty cool. So we did it. We kind of found a model reaction. So this model reaction was first reported, by Macmillan's group in Science about 10 years ago. So what they found is they found that they can do aeration reaction. So you start with this amine. You oxidize amine from alpha amine radical, and you have the cyanobenzene get reduced, and then form this anion radical, and then they do this radical coupling to form these aeration products. This chemical reaction can be done using AC because you can oxidize, use electrochemistry, you can oxidize these parts as your anode and reduce this guy as your cathode. But the issue here is, when you do this reaction using electrochemical reaction setup, you're going to end up with a lot of cyanation products because this, alpha amine radical can get further oxide to iminium, and iminium can get nucleophilic attack and then phonous cyanation product. So it looks complicated, but don't worry about it. And so I have a simplified version for you as well. So in my eye, it actually is, you can simplify this, selectivity problem in as follows. So you start with A, right? So if you electrochemical oxide A to A plus dots, and you do some chemical, reaction, which is depollination, remove the positive charge and the A dots. If you stay as A dots, and you can perform radical coupling reaction against this aeration product, or you can first oxidize these A dots to A plus. And A plus can do nucleophilic attack and phonous cyanation product. So at the end of the day, the two product selectivity issue here is truly coming from how to control the reactive intermediates. Do you want to stay at A dots or you want to harvest as A plus? How can you control that? As you can see, there are two electrochemical steps. So, the easiest way to do that could be if these two reactions, electrochemical reactions, requires different potentials, and especially the second one requires high voltage or high potential, then we can just lower the potential and shut down this electrochemical step so that we can harvest the A dots and get the cyanation products. But I can tell you it does not work, okay? No matter how you change the voltage and lower the voltage, the cyanation product is always dominant. And then the aeration product is always the minor product. The reason for that is, this oxidation of, the amine and the radical, they actually happens at comparable potentials. So here's the results here showing that's the case. So without any base, this amine can get oxide twice. This is the first one, oxidation, oxidized to phonous cation radical. The second one is phonous iminium. But with base, you can see these two peaks merge. And the first peak becomes pretty big. This is because the first oxidation here, and you only have a base, you immediately phonous radical, and a radical can immediately get oxidized on the same potential. That's why the peak increases. So that's why no matter how you change the potential, you will always over-oxidize your product. Oxide, radical to iminium to get you the cyanation products. So it's not gonna work. So how can we do to achieve the selectivities here? How can we shut down this second step? And then we realize that if this three step here actually is sequential, which means you have to perform the first one, then you can perform the second one, and only after you're done with the second one, you can do the third one. So they have this kind of sequential, kind of a property. So if that's the case, can we temporarily separate, these two oxidation steps? So what if we have a really slow chemical step and we apply a short oxidation pulse and just oxidize these A to A plus dots? And then because the chemical step is slow, so that's, A plus dot don't get easily deprotonated to A dots during this plus, potential here. And then we immediately flip the potential to the reducing environment. In the reducing environment, the chemical step will not be effective because this chemical step has nothing to do with the potential you applied. And you can form A dots here, right? So if you form A dots here, and A dots will not be get further oxidized A plus because nothing can get oxidized in a reducing environment. Okay, then we can trap over A dots in this negative pulse here. So we tried it. So my students varied the potential, the frequency, and what she observed is, as DC condition, the cyanation product is dominant, but when when you tune the frequencies, when you add 10 hertz, the selectivity completely flipped. It just, when you just simply tune the frequency, you really can suppress greatly the cyanation product formation and then promotes the aeration product formation. So 10 hertz means, you just apply a 50 millisecond of pulse of oxidation and 50 millisecond of negative potential, right? And then because this is optimal, that means, under this kind of 50 millisecond pulse, most of the oxidation, of the depollination will not be able to happen, okay? This is what the 10 hertz means. And then, when you have low frequencies like that, then the depollination can happen at the anodic environment. Then you can, form this radical, and the radical get further oxidized to iminium. Then it gets a lot of cyanation products. At higher, yes, even higher frequency, right? Yes, you probably will not be able to, deprotonates your cation radical, but the cation radical will be, carried over, to the next positive cycle. So like reducing environment still, will not be, further oxidized, but if the process is slow and then you enter the second period, you can get further oxidized from this kind of iminium, and you get a worse, selectivity again. So we call this the carryover effect. Okay, so now we have found that there is truly an optimal frequency for controlling the the selectivity, and then we was able to find that by screening a whole bunch of frequencies. But that's just not a very effective way to do it, because it took my student a long time to find out the optimal frequency, because every reaction requires separate power supply. The frequency dependent study took her entire week to complete. So we start off the question: can we rationally design the optimal frequency? So if we think about really carefully, you realize surely what we consider here is we are considering A get oxidized to A plus dot 1 electron process, or is A gets further oxidized this to form this A plus, this 2 electron oxidation process. And then if we had the same starting material and then one go into 1 electron oxidation, the other one go into 2 electron oxidation, you can easily tell that in a CV, because when you have more electron being taken away from a molecule at the same concentration, the peak current should be higher. So actually, we developed a really simple way to predict the optimum frequency using secondary voltammetry. So what we did here was, we start with this kind of a reference here. This is the record is the reference curve. It just shows the 1 electron oxidation, reduction reversible process, and then as a reference point. And then, if our starting material main, right, and then we put the base in there, and at low frequency, you can see the peak is shifted and the peak height is larger than the reference point. That means you are oxidized that molecule by more than 1 electron, which is not what we want. We want to stop at 1 electron oxidation, right? But the cool thing here is once you increase the scan rates, this peak height will decrease, and then the two curves start kind of merging at about 5 volts per second. The first segments of these two curves complete overlap. That means from here to here, there'll be no 2 electron oxidation process, just 1 electron oxidation process. So what does that mean? So from here to here is about 220 millivolts, and we're scanning at 50 volts per second. So time that's not can involve any 2 electron oxidation is about 44 milliseconds. Okay. In other words, if we apply a 44 millisecond pulse, oxidation pulse, you will have no issues with further oxidation by 2 electrons. So this 44 millisecond will be equal to about 88 millisecond period time, right? Or you convert it, it's like 11 hertz. So 11 hertz is in an excellent agreement with what we had previously experimentally found is 10 hertz. It's very exciting, and it means a lot, because when we were doing this trial and error optimization of frequencies, it took us several days to complete one substrate, and every substrate will be different. And it's like if I have a substrate scope of 30, it will take us like half a year to complete the substrate scope of 43 reaction, which is not it's not fun. But for now, we developed this Russian design method. It would take about several minutes to run the CVs and find out what's the best frequency we should use. But again, this is just one example showing that we get some agreement between CV predicted optimal frequency experimentally discovered ones. But we still need to validate our methods. So we take different substrates, run CVs without base, and then find out the optimal frequency based on the CVs. And then we carry experiments with predictive frequency and do a comparison. See if the predicted frequency is truly the experimentally observed optimal frequency. So for example, this guy here, we run CVs, and we found that as about 100 volts per second, or equivalent to 122 hertz, we get the best overlap here. And then we tried some frequencies, different frequencies near this optimal frequency. You can see when you have lower or higher frequencies, it just gets worse selectivity, right? And then we test a lot of them. We test about 30 different substrates, and then we found a perfect agreement between predicted frequency and experimental observed optimal frequency. Let's truly validate our prediction method. And then if we have different base, then the frequency will be different as well, because you have different base, the depronation kinetic will be different. Of course, the optimal frequency will be different. And then we saw that's also varied by field order magnitude. And then another thing that we found is when we were doing this kind of experiments, we only use the sine wave, right? And the best condition we got, result we got is like 70 to 16. So selectivity is not ideal, it's not perfect. Now that's probably because for our sine wave, you have some continuities here. You have big high voltage, low voltage is continuous. So actually we tried some like 3-stage waveforms, and that's why I actually give you perfect selectivity towards these kind of cynation products selectivity. And there's a lot of room for understanding these kind of different waveform effects, and we're still working on it. Okay, so this is just one demonstration, and I think we have a lot of much broader impacts. So the reaction we demonstrated is just a mean oxidation to to control a mean oxidation to alpha mean radical, or 2-dimensional oxidation to a median, right? It's kind of similar. This kind of a ET-PT, ET process is very common in electroorganic synthesis. So for example, this method, A-rings oxidation, you also have this electron transfer, proton transfer, electron transfer process. By using our AC methods, we can probably harvest the radical over the cation intermediates and achieve selectivity changes. Another thing here we can potentially do is, as you guys can kind of notice that for different means, the optimal frequency varies dramatically. That means at different frequencies, you get your alpha mean radical. So these are just simple molecules. What if we have Jacob molecule that have multiple alpha mean sites? Okay, we will be able to activate different sites at different frequencies. That'd be really cool, because that means we can selectively activate different mean CH bonds by at different frequencies. So this is something we want to demonstrate. So we kind of demonstrate that on this hydrogen isotope exchange reaction. For you guys who are not familiar with this reaction is a fairly kind of straightforward. It's just like you have a drug molecule, you have a lot of CH bonds and hydrogens, and what we're trying to do is we're going to replace the hydrogen with deuterium and tritium. Right. The reason why you want to do this is because these labeled drug molecules are very useful for diagnostics in drug discovery, and also is very useful for synthesized deuterated drug molecules. So here's just some examples here. It's just like if I have a deuterated drug molecules versus the undeturated, you have some mass shift on the mass spec results, and you can tell this is a drug molecule. And also if a radioactive tritiated drug molecule, you can see where how a drug molecule undergo metabolism in your body. And then the deuterium ones, they kind of replace some CH bonds with CD bonds and change the property of the drug molecule. And then for this application, they want to have site selectivities. So we want to see if our AC dependent frequencies can be applied to achieve these selectivities in hydrogen isotope exchange reactions. So first of all, I'm going to introduce some classic, hydrogen isotope exchange reaction. So this is a method developed by Macmillan's group and Merck, about I think 4 years ago. So what they did here is they did this hydrogen isotope exchange at the alpha mean position. A similar chemistry is like you have this amine, and you do photo oxidation from this alpha mean radical, and you have thiol, deuterium thiol, and then transfer deuterium atom to this alpha mean sites, and it ends up deuterated product. But for these methods, it kind of label all the alpha mean sites with no selectivity, and gets pretty high in deuteration. So what we want to do is we want to try to achieve different selectivities. Here's what we're thinking here, because the similar transformations we have here in the full readout cycle can be potentially done using electrochemical method. So we can oxidize this amine to form this cation radical, and then we can do deprotonation to form this alpha mean radical, and then we can do hydrogen atom transfer to form this deuterated drug. Okay, and then because we have AC, right? So if I apply AC, and I can control how long I want to oxidize this guy and then reduce it back. Okay, that's kind of interesting part because you have electrochemical step and two chemical step and a reverse electrochemical step, right? And then these two steps actually can vary by the kinetics rate constant can vary by several order of magnitude. So just imagine you have a really slow step here, and then we oxidize it, and then it takes a long time to complete the two chemical step, and it gets the products. And I don't let them to have enough time to do that, and I immediately flip the polarity. Then this this cation radical will be converted back. Okay, and if you have some sites that can easily undergo these two chemical steps, they get deteriorated. So we can, by controlling AC frequency, and we can control the deterioration site. So to demonstrate that, we kind of first start with some simple molecules. So we have two molecules here. One is the pyridine, the other one is THIQ, the tetrahydroisoquinoline, or THIQ, this molecule. So these two here, they have quite different deprotonation kinetics and hydrogen transfer kinetics. So what we're trying to do now is we want to apply voltage, positive voltage here. We oxidize this cation radical, and then we deprotonate it, and then we just do hydrogen transfer with the detunate the thiol, and then this thiol radical get regenerated and do the same thing here. So this is the hydrogen transfer catalysis regeneration here. And we think for these two molecules here, the KPT and the KAT have different rates, and then that will lead to different optimum frequencies for the detonation of these two substrates. So before we did any experiments, we start kind of estimates the time or rates constants, the rate constant for deprotonation and for HAT kinetics. So because the HAT kinetics, hydrogen atom transfer kinetics, depends on the bond dissociation energy at these different sites. So actually we kind of calculated the bond dissociation energy for these ABC sites. And it turns out if we want to do hydrogen atom transfer, as A sites is much slower than the rest. You can see this is just 1. We normalize it, so it's 1 for these C sites is 10 to the 5th. And the same case here. If we compare A and D, they are like 30,000 times different. So the hydrogen atom transfer at these sites is much faster. And then also we kind of estimate deprotonation kinetics. So if you want to if we have a cation radical here, and if you want to deprotonate A site versus D site, the rate is about 20 to 1. So as I said, if you want to do this determination on this kind of alpha amine sites, you have to do two chemical steps. One is deprotonation, the other one is hydrogen atom transfer. Okay, so based on the numbers here, we can expect that the if we want to hydrogen isotope exchange for molecule 1, we require much longer time or low frequency, because the hydrogen atom transfer to these sites is very slow. But for 2, it can occur at high frequency because deprotonation is not too bad, not too much slower, but the chemical step for the hydrogen atom transfer is super fast. So we just want to see if we have these two model substrates, do they happen to, does the hydrogen isotope exchange reaction happen at different rates? So we tried it, and the result shows that's the case. So for this THIQ substrates, we don't guess anything when you have hertz, frequency larger than 0.5 hertz. And we get the best result when we don't have any frequency. Just as we expected, the hydrogen atom transfer here is really, really slow. Okay. And then, for the, the pyridine, you actually see here, when you have DC conditions, it's usually really bad. And then you have really high frequency, kind of deterioration, even as 50 hertz per second. Just like we predicted previously, when you have really slow chemical steps here, your deterioration cannot finish. This guy will be converted back. But for this guy here, the pyridine, the chemical step is relatively fast, especially hydrogen atom transfer really fast. So once we generate this cation radical, they can directly go to a product, right? So even you have high frequencies, it's not going to convert it back. And we actually kind of did some, analysis of the, the product, and then we kind of found similar results. You can see when you have your, this is the THIQ results. On the DC conditions, you have the highest deincorporation, and for pyridine, as high frequency gets the best results. So this just demonstrates that, when you have different alpha mean sites, you truly can use frequency to control the deuteronation process. And then based on our result, we actually can estimate the time scale for different steps. It turns out for molecule 1, which is the THIQ1, the proton transfer only happens about 50 milliseconds, but for hydrogen atom transfer, it takes about 20 seconds to complete. But for molecule 2, which is a pyrrolidine, it's about 2 seconds to finish the deprotonation, and less than 3 milliseconds to finish the hydrogen atom transfer. So the experimental determined ratios is 40:1 and larger than 6,000 to 1. It's just in excellent agreements with the predictions. So with that, I just want to show you kind of thanks the student who did the work. So Sachini and Disney and Jyoti, these three are kind of organic subgroup. They did almost the work, and also Nibata here. And I also thank the collaborators we have, and then all the funding agencies. And then thank you for your attention. I'm happy to answer any questions.
Thank you so much for your wonderful talk. So students and the postdocs can ask questions firstly. Maybe I can ask question first. I hold a very general question. So from my perspective, I feel there are two ways for the electrochemistry, and there is a method like to develop a new catalyst to achieve higher performance, like higher Faraday efficiency or higher normalized reaction rate. And for the AC electrolysis, I feel it can achieve higher selectivity by like shutting down further oxidation or reduction reactions and perform the cathodic and anodic reaction at the same electrode to secure the energy efficiency. However, at the same point, at the same time, I feel these two methods are kind of parallel because of the stability issue of catalyst at too high opposite potential. So I just wondering if it's possible to find a cross point between these two methods, like involve both heterogeneous catalyst design and AC electrolysis together to achieve the scale up of this method.
Yeah, that's great. Great question and a comment. Yes, this is actually what we're trying to do now, because so far, in our design, we did not really kind of synchronize catalytic cycle with our AC kind of cycle. But I think there's a huge potentials there because typical, think about a typical catalytic cycle, right? So you're turning over the catalyst, and then the turning over the catalyst depends on the reactants you have, or probably the potential you applied as the electric surface. And then this is kind of fix the concentration of intermediates or the different states of catalyst. But when you have AC, you actually can tune the ratios to reactive species of your catalyst, and then can further control the selectivity as well. So yes, this is something that we're trying to do. We're trying to use the AC to modulate the catalytic cycle and it gets different selectivities.
Okay, thank you so much. Any other questions from students or postdocs? And the professors also feel free to ask questions if there is no questions from students.
Okay, maybe I can ask a general question.
Yep.
So the reactions you're doing, not that there is no value in this. I think there's a lot of value. But like they seem like they can be done by other means. Right? So what's your dream reaction that you can do with this?
So actually, the dream reaction we are trying to do now is just do the site-selective hydrogen isotope exchange reaction, because there's just no strategy out there to selectively label different alpha mean sites. So like whenever you do this, you would typically label multiple sites at the same time. It's difficult to selectively active one site, and then not touching the rest. It's very difficult to do it. but with the frequency, we have a possibility here.
Mhm.
But you can see, so when we first saw this kind of optimal frequency, plots, we were really shocked because we thought that's very similar means, right? And then, but you can see the frequency, variation is huge. It's over almost 3 orders of magnitude. Okay, sometimes you just have small, function group difference. This frequency, optimal frequency vary by 1 or 2 orders of magnitude. That gives us a lot of room for tuning and selective, activates one amine site.
So have you thought about, if you can activate this selectively, have you thought of functionalization? So beyond labeling, which is a way of functionalizing the site.
Yes, exactly. This is what's going to do. So yeah, once you can select activate one site, now we just do hydrogen atom transfer to put deuterium there or tritium there, but it don't have to be, right? So you can add other reactive species. You can do radical coupling. So you can selectively activate different sites. That'd be really cool.
Yeah,
and this is just
very interesting. Yes.
Yeah.
Yeah, no, I think you are doing a lot of reactions that involve a lot more organic synthesis that none of our electrochemists except you is here. and you actually is doing a lot more organic synthesis of electrochemistry these days.
Yeah,
So
I'm not really organic chemist.
impressed.
It's like, I also, always joke with my organic colleagues, I have difficult time remembering all these organic names. But it's fine, my training was like physical
they should put less emphasis on remembering names too.
So
it should be by now a bygone from a very self-centered era.
Yeah, I told them, to me, it's just a name or symbol. I can replace with A, B, C, D. It doesn't matter to me, really.
Yes. Yeah. But very nice work. Thank you. I'm really glad we had you for a webinar. I hope somebody else has questions, although it looks like a lot of people left. And I think I just realized I insulted Alex, who also does electrochemistry, and he is a bona fide, synthetic person. But Alex, you can take me on.
It's all good, Paula. No offense taken whatsoever.
I think, Alex, I think what I'm trying to say is, I think you spend a lot more time with what we call the small molecule activation in inorganic chemistry. So yeah, this is pretty impressive. Yeah. Other questions? Okay, well, I think we can stop here with the scientific part, and maybe you can hang out for a few more minutes. We chit chat a little bit more. I tell you that you look like a high school student. I've been staring at your picture outside my office, and I'm like, I cannot believe you're a professor already. So
I actually have a Los Angeles.
Yes.
My body says the